All right, and away we go. Okay, so welcome to week 2 of stats as we continue on our look at chapter 2. So last time we met, we looked at measures of central tendency, such as the mean, the average of a series of scores, and we also used that idea and the idea of deviations to calculate standard deviation, or how variable or spread out scores are. And today we're going to use both of those concepts to calculate a very important concept, a very important tool for statistics, which is called a z-score. So these are a special set of scores. These are specially transformed scores, and we're going to see that they are massively useful in statistics. Now, before we get to that, just a few words on the upcoming exam number 1. So exam number 1 is going to be next time that we meet, May 22nd. It is going to start at 10 a.m. So we're not going to start right at the beginning of class. We're going to have the exam in the second hour of class. It'll start at 10 a.m. It's only going to cover chapters 1 and 2. So it will cover just the concepts that we've introduced in those sections. It will cover, there will be no surprises whatsoever. And importantly, the kind of questions that you're going to be seeing on the exam are computational. So it's a completely computational exam. What that means is that you're not going to be asked, what's the definition of this? You're not going to be asked, explain the average to somebody who hasn't taken a course in statistics or anything like that. All the questions will be calculation questions. You'll be asked to calculate the mean, calculate standard deviation, calculate deviation sum of squares, calculate, sum square deviations, calculate z-scores. It'll all be calculation for the exam. So consider that when you're preparing yourself. As long as you understand how to calculate these concepts, even if you might not understand the intricate nuts and bolts of conceptually what these concepts are, as long as you can calculate them, you can get perfect on the exam. So the entire exam will be done in Canvas. It's going to look just like your practice Excel sheets. So you'll have the question, there'll be more of an explanation in terms of what you need to do, but then you'll have your raw data, your scores, and then you'll have your answer cells, the yellow answer cells where you put your final calculation. The only difference is that it won't have those automatically updating green cells that let you know when it's correct. So I'll be grading those, I'll be adding those in later, but that's what will be going on with the exam, just like the demo practice Excel sheets that we've done in class. There's going to be 7 questions, and none of the questions should be any sort of a surprise. So you will have questions where you do order of operations. So there'll be questions dedicated to order of operations and the summation symbol. There's going to be questions dedicated to working with a frequency table and a frequency graph. So you will not be asked to create frequency tables or frequency graphs. You will be given frequency tables and frequency graphs, and you'll need to answer questions about the scores that make up those tables and graphs. You will also be calculating the mean, the median, and the mode. You will be calculating sum squared deviations, standard deviation, and variance. You'll only be doing those for samples, and that will be explicitly mentioned in the exam as well. And then finally, what we're going to see today is you're going to be calculating z-scores and standardized scores, and that's the entire exam. So there shouldn't be any surprises to anyone. This is all stuff that we've seen before. Just want to see that you can do it on your own in this exam situation. All right, so do remember that the exam is not a memorization exam. This is open book. And what open book means, it means open anything that you want to use except other people. So if you want to access your textbook, feel free to do that. If you want to go and access the lecture notes, the student lecture slides in Canvas, feel free to do that. If you want to Google how to calculate something, feel free to do that. If you want to open up your old Excel sheets, you can do that as well. If you want to make yourself little notes, little step-by-step guides on how to do this, feel free to do that as well. anything that you need in order to do this exam is permitted. The one restriction is you cannot talk or communicate with other people. So your cell phone will be away. You can't Skype with the chair of the stats department at MIT. You can't do anything like that. Has to be your own work. But whatever you need in order to get it done, feel free to do that. So if you want to come in here with a list of Excel equations written out on a paper for yourself, do that. All I want to know is, can you calculate these things? Whether you got it all stored up here or stored down here, doesn't really matter, but can you do those calculations? So remember, that is there to kind of help you to remove you from having to memorize any of these formulas or ideas. However, do not think for a second that you'll have enough time in the exam to learn these concepts. So if you don't know what a particular concept is, open book is not going to save you. So if you still don't know what sum of squared deviations are, and you're asked to calculate it, an open book resource is not going to help you. You're going to take up too much time trying to figure out what it is. So come prepared, but also prepare your materials as well so that you can get 100% on this first exam. And then the last thing that's mentioned there is that this must be completed in class. And because it is distributed via Canvas and you upload it via Canvas, I just don't want there to be any confusion that you can take this at home. I need to make sure that you're doing it in an exam situation, i.e. that you're doing it on your own, that you're not communicating with others. So it needs to be done in class. There'll be assign-in sheets for that purpose. So I just want to make sure that everybody is clear on that up front. All right, any questions on exam number 1 and what to expect? All right, so exam number 1 starts at 10 a.m. What we're going to be doing at 9 a.m. is we're going to have a review session. So Wednesday the 22nd at 9 a.m. there'll be a review session for exam number 1. This is an open review session, and what I mean by that is that it's number 1, student driven. That means that I will be here ready to answer any questions, ready to do any demonstrations, ready to show you anything that you need in order to get ready for exam number 1. But I will have nothing prepared in advance. Everything that I want to cover will finish today. So it's going to be student driven. Bring your questions to class. Ask to see things. Ask for explanations in class. I will respond basically to what you want to see. So come with those, anything that you want to see. Again, it'll be completely student driven. And because of that, it's also optional. So if you feel that your 9 to 10 a.m. would be better, you'd be better off preparing in another way. If you feel you'd be better off grabbing another hour of sleep, whatever you think you need to get ready for exam number 1 to do the best that you can, feel free to do that. I will be here from 9 a.m. to 10 a.m. to answer any final questions that students might have. All right, any questions on that before we start up on today's Z-scores? Oh, the exam is 1 hour and 15 minutes you'll have for the exam. And then after the exam, we won't be doing anything for the 3rd hour. So the 3rd hour will be your break from the exam. I really don't like to lecture after an exam unless it's absolutely necessary. So from 10 to about 10:15, we'll have the exam. And then after that, from 10 to 11:15, we'll have the exam. And then after that, we won't have class. Any other questions? All right. Okay, so what we're going to do today is we're going to continue building these fundamental skills, these basic concepts that we're going to use throughout this semester. And we're getting much closer to the time when we can actually start doing a lot of the cool things about where we can analyze psychology data, analyze psychology experiments, treatments, things like that. But we still got to put in the work. We still got to put in and build on the fundamentals. And today we're going to continue that with Z-scores. So I'll set it up with an example here. One of the ways that Z-scores can be very, very helpful. So let's say that you're a clinical psychologist. You deal with developmental children issues. And let's say that a child is brought to you and the mother is saying that, well, my child seems to have some behavioral problems. My child seems to be just very active, massively active, can't sit still, can't sit down, can't take a break, extremely active. and also has poor attention, right? Cannot focus, cannot attend to a particular task, gets distracted very easily, and they want you to, help this child. One of the things that you'll find in clinical psychology is that oftentimes patients present with multiple syndromes. It's called comorbidity. They oftentimes suffer from very many different issues. And one thing that you don't want to do is try to tackle them all at once. Because if you tackle them all at once, it'll be very difficult for the client to make any progress whatsoever. So as a clinician, you would want to identify what is the biggest problem? What are they suffering from the most? What is the most extreme behavior? So we would want to test whether or not their activity is their most extreme behavior and then tackle that one first, or is their lack of attention their most extreme behavior and we'll tackle that one first. Which one is the greatest problem? Which one are they the most extreme on? That's what we're going to be using to illustrate the power of z-scores today, and just how useful they can be and why they're so widely used in psychology and statistics and so on. So we'll have our introduction to z-scores, then we'll see how to actually calculate these z-scores. We'll talk about the properties of z-scores, calculations of raw scores from z-scores, and how to get a very useful concept of standard distributions. And then we'll talk about the homework assignment. And remember, there are some weird due dates, due times coming up because we're having our first exam on Wednesday. All right, introduction to z-scores. What is this all about? So let's imagine, going back to that child that we're treating, let's imagine that I develop a test, much like an IQ test that measures intelligence, but this one measures activity and it's called the active Q. And this client, this child, his name is Jimmy. Let's say that he scored an 80 on the active Q. That 80 in and of itself right now is meaningless. Because if I said, oh, he scored 80 on the active Q, does that mean that Jimmy has a high active Q? Is that higher than the average in the population? Or is that actually a low active Q, right? Is that actually lower than we would expect? Is that lower than the average in the population? And with just that one number, with just that 80, we have no idea. The way that we answer this question is if we can place his score on a distribution of scores. So these were the scores, and that is the distribution of active Q scores in the population. Well, in this case, for this distribution, Jimmy's score is right there, and you can see that he is above average, right? There is not a lot of individuals here, this little section here, that score higher than Jimmy in the population. Most of the distribution is below Jimmy in the population. So this is pretty extreme. He's higher than most people. That would be his situation for an active Q score of 80 for this distribution. But what if that's not the distribution? What if that was the distribution, right, with these particular scores? Well, if that's the distribution, then Jimmy actually has a very low level of activity. His mother has misperceived how active a child should be, and Jimmy actually doesn't need to be less active. Jimmy actually needs to be much more active. So that score of 80 is meaningless, right? Means nothing to anybody until you can put it into a distribution. And z-scores are one way to put a score into a distribution. All right, so that was his active Q. Let's say that Jimmy did score 80 points above the mean on his active Q. 25 points above the mean on his active Q. Let's say that this was the distribution that was the actual distribution. So he scores 25 points above the mean, but remember that he also has attention problems. So let's say that I also developed an ADHD-Q test to assess attention, and we give it to Jimmy, and Jimmy's ADHD-Q score is right there. It's a 70. So he gets 70 on the ADHD-Q. The question is Jimmy more extreme? Are his scores more extreme for the active Q or for the ADHD-Q? Because remember, both of these come from different measures. And it's right now, it's like measuring, comparing apples and oranges. We have an ADHD Q score, we have an active Q score. We know from elementary school mathematics that 80 is higher than 70, but what does those scores actually mean? So again, we can't answer this unless we can put it into a distribution. Because even though 80 is higher than 70, if that is the population distribution for the ADHD Q scores, well then we can see that Jimmy is very extreme in the amount of, or in the lack of attention. So comparing those distributions side by side, we can see that even though 80 is higher than 70, and again we learned that in elementary school, notice that Jimmy is pretty high on his active Q, but he is literally one of the highest people in the population, one of the most extreme scores in the entire population for ADHD Q. So this means that his ADHD Q is much more extreme, much more out there, much more of an issue than his activity, and we would want to start treating his attention first and then move to his activity. So again, all of this was problematic. These comparisons, this evaluation was problematic because we were dealing with two different measures that had to be put and compared to two different distributions. So if we want to understand and compare scores, which we do in psychology a lot, we are very complicated beings. We got a lot of things going on, and we do often want to compare how are we doing in this situation compared to this situation. Well, if we want to do that, then we need a way to describe scores with respect to a known distribution. We need to be able to describe scores with respect to a distribution that has features in common with other distributions, and that is where z-scores come in. All right, so that's why we need z-scores. Let's see what they actually are. So what a z-score is, it's just a transformation of your raw scores. So you have your x scores, you have a set of raw scores, let's pop those in right here. So we have a set of raw scores, and all z-scores are is a transformation of those raw scores. So in this case, we take these raw scores, and I'll show you how to do this in just a moment, but we would transform them into z-scores, and it's a concept that we use every single day. So if you are weighing things, you can weigh them in pounds, but then you can also transform that into grams, right? Or you can transform it into ounces. If you have money, if you have US currency, you can transform that into yen. You can take your yen and transform that into euros. You can take your euros and transform them into pesos. This idea of changing them into a different scale is something that we've experienced before. We're doing it now, just in a very, very special way. So what does this transformation do? What's so special about it? Well, what it does, kind of conceptually, is it takes whatever distribution that you have, and it moves it and stretches or squeezes that distribution so that it has a very specific characteristics, so that it has a very specific mean, and it has a very specific standard deviation. So what it does is if we have this distribution right here, and those are our raw x scores, if we were to calculate the z-scores, it would take our mean from about 7.7, which is right there, and we would move the entire distribution and squeeze it so that our new mean for the transformed scores has a mean of 0, and our standard deviation is equal to 1. And that's what a z-score does. It takes your entire distribution, squeezes it down so that you have a standard deviation of 1, and puts it so that the mean is at 0. If we have this distribution over here with this mean, a mean of about 6.2, calculate the z-scores. This time the z-scores will stretch it out so that the standard deviation is equal to 1, and once again move it so that the mean is equal to 0. And it does this for any distribution. So we have this distribution here, has a mean of about 5.2. Z-scores would take this distribution, squeeze it down so that standard deviation is equal to 1, and then move it so that it has a mean equal to 0. And the great thing about z-scores is it does not matter what your distribution looks like. Every distribution has variability. It's got some amount of spread. Every distribution is going to have a mean, and z-scores will take that distribution, stretch it or squeeze it down, and then move it so the mean is equal to 0. That's what a transformation into z-scores actually does. All right, so far so good? Okay. So what a z-score then does, because it sets your mean at 0, because it sets your standard deviation equal to 1, it specifies any single score in terms of a known distribution within a specific distribution. So a z-score consists of 2 parts, and those 2 parts give you all the information that you need for a particular score. So the first part is the sign. A z-score will have either be positive or negative, and if a z-score is positive, that means it's above the mean, and if a z-score is negative, that means that it's below the mean. So let's say that a friend of yours took a test, and you ask them, how did you do on the test? And they say, oh, I got 27. Did they do well? Did they do poorly? It completely depends on what the test is out of, right? If it's out of 100, they did very poorly. If it's out of 30, they did very well. You don't know until you get more information. But if they told you that, if you ask them, how did you do on the test? And they say, oh, I got a z-score of 1.5, then you know immediately, oh, positive z-score? Well, you did better than the average of the class. Congratulations. If, on the other hand, they said, oh, I got a z-score of -2, then you would say, oh, well, I don't know what your test was out of, but -2, that's below average. Maybe we can study a little bit more next time. Maybe we'll turn it around for the next test. So a z-score immediately lets you know, are you above the mean or below the mean? The way that, again, that 80 score on the active cube told us nothing, a z-score tells us positive you're above, negative you're below the mean. And then the other part of it is the actual number, the actual size of the z-score. And what that tells us is it tells us the distance from the mean in terms of standard deviation steps. So it tells us the difference from, the distance from the mean in terms of how many standard deviations away from the mean are you. So that positive 1.5 z-score means that not only are they above the mean, but they are 1.5 standard deviations above the mean, right? 1.5 steps, standardized steps above the mean. And if they say, oh, I got a z-score of -2, that means that they are below the mean, and they are 2 standard deviations, 2 steps below the mean. So it tells us not only whether we're above and below, but how far above and how far below in terms of these standardized standard deviation steps. And remember, those steps are equal to 1, because that's what a z-score does, makes a standard deviation equal to 1. So in this one number, that one z-score, if somebody tells you, I got a z-score of, let's take a look at one of these, -1.71, you immediately know below the mean, and you immediately know 1.71 standard deviations below the mean. If they tell you, I got a score of 11, 11 is meaningless. We don't know what 11 means. But if they tell you, I got a z-score of 1.33, we know immediately above the mean and 1 1/3 steps above the mean. So z-scores, very, very useful in determining exactly where somebody is in a distribution. All right, so that's the background of the z-scores. Let's take a look at how we actually calculate these in theory, and then we're going to take a look at how to do it in Excel coming up. So in theory, the formula for transforming any raw score into a z-score, for a population, to calculate that z-score, you take the raw score minus the population mean, and that is your deviation, right? Remember that deviation is your raw score minus the mean. So we take the deviation and we divide it by the standard deviation. So we take the distance from the mean for every single score and we divide it by the standard deviation. That distance from the mean is what makes the average of z-scores equal to 0. And that dividing by the standard deviation is what makes the spread of the z-scores equal to 1. That standard deviation is equal to 1. So that's the two parts of it for a population. For a sample, exact same type of formula. We have the deviation, your raw score minus your sample mean, all divided by your sample standard deviation. So once again, we take the deviation, how far away are you from the mean, and then we divide it by the standard deviation to standardize the step size to get to that particular score. All right, so let's continue on. Again, we'll see how to calculate, use this formula in Excel so you can calculate z-scores rather quickly. What we're going to do right now is we are going to take a look at properties of z-scores, continue on with that. So z-scores, they are transformed scores. They are your transformed x-scores. So why are they useful? We've touched on this already, but let's just make it explicit. They're very, very useful because they tell you the exact location of your raw score within its distribution. They tell you exactly where that score is within its particular distribution. And they can also help you form a standardized distribution or a standard distribution. So z-score is a standard distribution that allows you to compare a z-score from one measure with a z-score from another measure, right? So it allows you to compare basically apples to oranges. So again, this is sort of what we've seen. I'll give you an example from everyday life. This is like comparing money, right? Comparing the cost of things in different countries. So if in one country they say something like, oh, a watermelon, in Japan costs 200 yen, and a watermelon in Italy costs 3 euros, right? I'm making that up. I don't know what those are, but anyway, 100 yen in Japan, 3 euros in Italy. Where is watermelons more expensive? Well, you can't answer that, right? We got to get them on the same scale. So if you transform yens into US dollars and euros into US dollars, then all of a sudden we can compare those two different types of monetary values. Same thing with a z-score. You can take two completely different scores from two completely different distributions, transform them into z-scores, and all of a sudden you have them on the same scale. You got them in the same units, and you can compare them. So if you were an educational psychologist, and you were working in high school, and a student comes up to you and they say, you know what, I don't know what I want to do with my life, I don't know where my skills are, I need some guidance, I need some help, do you think you can help me? And you're like, all right, well, let's take a look at your scores recently in some of your courses, and let's say that they were thinking about maybe doing English and maybe doing math, and they had a quiz, they just had a quiz, and the top distribution there are the scores of their class on the math, actually let's do that, English, so that's on the English quiz. The top one is their scores on the English quiz. The bottom ones here are the scores on the math quiz. Right? So we got the English quiz, we got the math quiz. And let's say that this student scored a 7 on their English quiz, and they also scored a 7 on their math quiz. So once again, we have a 7 on the English quiz, we got a 7 on the math quiz. Are they better at English or are they better at math? With just that information, we can't tell, because we're comparing scores on a math quiz to scores on an English quiz. It's not the same. They're not the same scores. But that doesn't mean that we can't do it, right? That doesn't mean that we are unable to compare these two scores. We just can't compare them when they're on different scales. So what we need to do is we need to take that score up there, the English scores, and transform them into z-scores. And we need to locate their score in those z-scores. And we can see that in that case, for their English scores, their z-score is just below 0. And then we take their math distribution, transform that into z-scores, find out where their score is there, and we on that distribution, and we can see that they scored about a 1.5 on their math quiz. So a 7 on the math quiz does not equal a 7 on the English quiz. 7 on the English quiz is below average, right? They're not that great at English. 7 on the math quiz is about 1.5 standard deviations above average. They're way better at math. And now we can compare their abilities on these two subjects because we put them into the same scale. We both put them into z-scores. So now we're comparing z-scores to z-scores, and that can be done. All right, so z-scores are transformed scores. They're transformed raw scores, raw values. What properties do they have? So we alluded to this before, but let's again just make it explicit. First thing, one of the great things about it is that z-scores do not change the shape of your distribution other than to stretch it or to squeeze it. So if your distribution had 2 peaks, then your z-scores will have 2 peaks. If your original distribution only had the 1 peak, your z-scores will only have the 1 peak. It doesn't change the shape of your distribution. It just squeezes it or stretches it out, but the basic shape remains the same. What other properties do they have? Well, the mean of your z-scores are always going to be equal to 0. That is one of its characteristics. So if I gave you a set of z-scores and I asked you to calculate the mean of my z-scores, you wouldn't need to go to Excel, you wouldn't need to pull out a calculator, you could just say 0. You know, the z-score mean is 0 because that is part of the definition of z-scores. The set of z-scores will always have a mean of 0. And then again, that comes from the fact that z-scores use deviations in their calculations. And if you add up deviations, we get 0 because the mean balances out your distribution. So basing it on deviations, that's why the mean of your z-scores will always be equal to 0. All right, the other property that they have, your z-scores will always have a standard deviation that is equal to 1. So if somebody, if you're reporting a set of z-scores to someone and they ask you, well, how spread out were they? What was the standard deviation? That person does not understand what z-scores are because z-scores will always have a standard deviation of 1. And that comes from the formula where we divide by the standard deviation of the scores to make that standard deviation equal to 1, to squeeze it down, or to stretch it out as needed. So z-scores keep the shape of the distribution other than squeezing or stretching it, always have a mean of 0, always have a standard deviation of 1. All right, any questions on anything we've covered so far on z-scores? Yep.
Would these still work if you had outliers?
Yes. So z-scores, it doesn't matter what the shape of your distribution is, it doesn't matter how weird your distribution gets, it doesn't matter how extreme a single score gets, your z-scores will always be able to you'll always be able to calculate them, they'll always have a mean of 0, and they'll always have a standard deviation of 1.
Okay.
Yep. Any other questions? Okay. So, the last thing we're going to introduce in terms of things that you can do with z-scores is you can you can always, but oftentimes you'll want to calculate your raw scores from your z-scores, right? So sometimes some people who are not statisticians, who don't understand z-scores, they don't want the z-score, right? They actually want the raw score. So if you were talking to somebody who didn't take statistics, and they ask you, oh, how did you do on that exam? How did you do on your stats exam? And you tell them, oh, I got a z-score of 1.5. They'll say, well, I don't know what that is. What was your percentage? Give me your raw score. Was it 80%, 90%? How did you do on that exam? So sometimes a z-score, even though it's massively useful, doesn't communicate what you want to other people if they don't understand a z-score. So we also have to know not just how to get z-scores from raw scores, but how to get back. So if you have if you have a z-score right there, how do we take that z-score and transform it back into the raw score? And it's really rather straightforward. It uses the exact same formula. All that you do is rearrange for the raw score there. So we just solve for your raw score, do a little cross multiplication, do a little moving of the mean off to the other side. And you can see that for any z-score, you can recover the raw score by taking the mean of the distribution the original distribution, taking the standard deviation of the original distribution, and then multiplying that standard deviation by the z-score. You add those two together, and you get your raw score. So if your z-score is a z-score of 2, your standard deviation is 10, and your mean is 100, that would be 100 plus 2 times 10. You would get 120 as your raw score. So you can recover your raw scores from your z-scores and go vice versa. Just the same way you can change American money into yen, yen back into American, American back into yen. You can do the same thing by transforming z-scores back into raw scores. And then the last thing that this allows us to do, that is also very useful, is it allows us to calculate and create on our own what are known as standardized distributions. So the z-score is a standard distribution, but we can also create our own distributions that might be helpful, that might be simpler to deal with than z-scores, and we determine what the mean is, and we determine what the standard deviation is. And the most common example of this standardized distribution is the distribution of IQ scores. Does anybody know what the mean IQ score is for a population? The mean IQ score for a population is 100. The standard deviation for IQ scores in a population is 15. So when they give you an IQ test, you end up with a large number of scores that get taken in, that get calculated out. And what they do is they then take your final score, your final calculation, and they transform it into a standardized score so that the population of people who take this IQ test have a mean of 100 and a standard deviation of 15. So it doesn't matter what year you're talking about, it doesn't matter what version of the IQ test you're talking about, the mean of it is 100, standard deviation is 15, and they do that by taking the raw scores from the IQ test and standardizing them, putting them into a standardized distribution. So there's 2 steps for creating these standardized distributions. The first step is you take your original raw scores and you transform them into z-scores. So it goes through the z-score distribution. So if we had these raw scores right here, we would take those, calculate out your z-scores. In this case, we got to squeeze it and move it over to where the mean is 0. That's your first step in creating a standardized set of scores for these raw scores. So the first step is transform it into z-scores. And then your second step is to transform it into your new standardized distribution that has a specific mean and a specific standard deviation. So in terms of IQ tests, they took their raw scores, changed them into z-scores, and then said, I'm going to take these z-scores and I'm going to change them into a mean that has 100 and a standard deviation that has 15. So you take your z-scores now and you transform them into a new standardized distribution that has whatever mean you want and whatever standard deviation you want. So you can literally transform it into any mean, any standard deviation that is either required or asked for or that you want. And that is the way to get to standardized distributions. So any questions at all on any of the z-score stuff before we have some in-class practice? Make sense? All right. So what we're going to do right now is I'm going to show you how to calculate z-scores very easily, very quickly, very efficiently in Excel. And then we will take a break and get ready for the second half of class. So we're back. Okay, so what we're going to be doing is we're going to be using Excel to calculate our z-scores, and we want to be able to take advantage of the copy and pasting functions in Excel. And the last thing that we're going to use, we're going to need that formula for calculating z-scores. So remember that a z-score is equal to your raw score minus your mean, all of that divided by your standard deviation. So if we want to start calculating out our z-scores, first thing we're going to need is we're going to need the mean of our, if we want to start calculating our z-scores, first we're going to need the mean of our raw scores. We're going to need the mean of those x scores right there. So we can do that just underneath. We go mean equals average, open your parentheses, highlight those raw scores, and we see the mean is 15.2. We also need the standard deviation. That's the other component of the z-score. So we go to standard DEV, standard deviation equals STDEV. We're doing sample, not population, so we can just use the backwards compatible old school formula of STDEV. We highlight our raw scores and we have our standard deviation right down there. So what I'm going to do next is the wrong thing to do, but I just want to illustrate what not to do. So you might say to yourself, well, here we go. We got our raw scores, we got our means, we got our standard deviations. We can put this into a column and calculate out our z-scores. So we go equals, open parentheses, because we got to do that top first. So notice that if we entered this into Excel, we could enter it in as your raw score minus your mean divided by your standard deviation. But if we do it like that, if we mention like that to Excel to do this, it's going to do it in the wrong order. It's going to take your mean and divide it by your standard deviation first, and then whatever you get there, it'll subtract away from your raw score. So to make sure that Excel is doing it in the right order, we got to use that order of operations. We got to put the deviation in parentheses in order for Excel to do that first. So we open up our parentheses, we highlight our raw score, and then from that we're going to subtract our mean, and then we close our parentheses, divided by, and then we're going to divide it by our standard deviation. So we get a z-score for that raw score of 20 of 1.75. We pop that into our answer cells using the equals function. We hit enter, and we see that we've got that correct. So we might say to ourselves, and this is the wrong thing to do, but we might say to ourselves, all right, well, that one worked. So I'm just going to copy and paste it all the way down. And immediately, things just go off the deep end. Immediately, things have gone wrong here. We're getting divisions by 0. Our formula has totally collapsed on us. And the reason for this is because Excel took our formula and took the cells that it was accessing and moved it down as we copied and pasted. So if we double click on that first formula, everything is going great. We're taking our raw score, and then we're accessing the mean, and we're accessing the standard deviation, and that's why that first one worked. If we double click on that second one, notice that it moved down one. So it moved down one, so it's accessing the right raw score, but now where it should be accessing the mean is putting in the standard deviation. And where it should be accessing the standard deviation, it's got a blank cell. So it can't calculate this out. That's why we get the hashtag divided by 0, exclamation point, warning sign. So we can't do it this way. We can't just copy and paste automatically the way that we might do with other formulas. So that doesn't mean that we can't copy and paste at all. What it does mean, though, is that we need to plan out a little bit beforehand. We need to plan out what I like to call parallel structure. We need parallel structures so that the information that we need to access in our formula is on every single row. So for example, we need an entire column filled with the sample mean for these scores, and we need an entire column filled with the sample standard deviation for these scores. So what we can do is we can say, all right, let's calculate the mean in this first column. So once again, we could calculate the average, average in the first column there. And we might say to ourselves, all right, let's highlight these, thank you, let's highlight these X scores over here, and we have the average. What we cannot do is we still can't just copy and paste that all the way down, because notice the averages change. And they change because, again, if we double click on these, we are missing raw scores if we just copy and paste that all the way down. In this case, we are now including the mean score in those raw scores if we copy and paste it all the way down. So we can't do that. We got the first one right, but we don't have any of the other ones right. And this is where the next trick that I'm going to show you, called the cascading waterfall, is going to come into play. What we want to do is we don't want to calculate that mean over and over and over again. That's not the power of Excel. We want to take advantage of the power of Excel and give it something that it can do over and over and over again. So what we're going to do is on that second row, we're going to make that second row equal to the first row. So we make the second row equal to the first row, use the equals function, and then just highlight that score right above it. And now we've made the second row equal to the first row. So how did that help us? Well, it helped us because this formula here is basically saying make this row equal to the row above. So when we copy and paste that, we're now telling the third row, make yourself equal to the second row. And if we copy and paste that into the fourth row, we're telling the fourth row, make yourself equal to the third row. Third row, make yourself equal to the second row. Second row, make yourself equal to the top row. Top row, you're equal to the mean. So we can do that and copy and paste that all the way down. And now we have an entire column of means very, very quickly. And incidentally, if you are looking for shortcuts so that you don't have to copy and paste every single time as you go down, one way that I like to do it is I like to highlight where I want to copy and paste everything. And then if you hold Control and press D, Control D means fill it all the way down, D for down. That will fill your entire column very, very quickly. All right, so we have a column completely of mean scores. We then have to do the same thing for the standard deviation. So once again, we go equal STDEV, open those parentheses, highlight the raw scores that we need the standard deviation for, hit enter. We've calculated out the standard deviation, and now we do that special cascading waterfall. We make the second row equal to the first, basically put in a function that says make this row equal to the one above, and then just like a waterfall, we copy and paste that all the way down. Whoops. And it makes our second row equal to the first, our third row equal to the second. It makes our sixth row equal to the fifth, fifth is equal to the fourth, fourth is equal to the third, third is equal to the second, second equal to the first, first is your standard deviation. And very quickly you get an entire column of standard deviations. All right, so is everybody at this point where you have a column of means, column of standard deviation? All right, so now we're ready to calculate our z-scores because we have this parallel structure. We have the components for the formula in every single row. So now we can go equals, open parentheses, highlight your raw score, minus, highlight your mean, close your parentheses, divided by, highlight your standard deviation. And if you find that you can't click on the standard deviation, you can always use the arrow keys to maneuver to one of the standard deviations. So we have our formula there. We got our our raw score minus the mean divided by the standard deviation. We pop that into Excel. We get ourselves our z-score. We pop that into our answer cell, and we have that done correctly. All right, I'll show you that one more time before we copy and paste this all the way down. So once again, equal, open your parentheses because you got to give Excel the order of operations. Highlight your raw score, minus, highlight your mean, close your parentheses, all of that divided by, highlight your standard deviation. We hit equal, calculates out our z-score. We got that one correct as well. We can see that. So now we can copy and paste that all the way down. And because we used this parallel structure, we know that it's accessing the right information. And if we double click on any one of those formulas, you can see that now that we've copied and pasted the formula with this parallel structure, we're still accessing the raw score minus the mean, all divided by the standard deviation. And if we pop those into our answer cells, you see that we have All of those correct. All right. So far so good. Does everybody have those numbers? Does anybody not have those numbers? Okay. So while some of you are finishing up that calculation, when you're doing your homework, you'll have these automatic grading cells available in your Excel sheet. However, oftentimes you won't have automatically graded cells. So in the real world, you will not have automatically grading cells when you're doing your work. In the exam, you will not have automatically grading cells doing your work. However, there is a nice way that you can kind of double check your work when you're doing z-scores to make sure that you didn't make any kind of manual human errors. And one way to do that is to take advantage of the mean and the standard deviation of a set of z-scores. So we can calculate the mean of the z-scores equals average, open parentheses, and calculate the mean of your z-scores. And if we've done this correctly, what should our z-scores be? What should the mean be? It should be equal to 0. So we can hit enter. We get this weird looking number right here. That is scientific notation, and that is the equivalent, that is Excel's way of saying 1.77 times 10 to the minus 16. And what that equals, it equals 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 177. All right? That's pretty darn close to 0. So we got that one correct. So we calculated the mean correctly. Sorry, we calculated the mean indicates that we've calculated the z-scores correctly. One more thing that we can do is we can calculate the standard deviation of our z-scores. Based on what we know about z-scores, what number should be there? Should be a 1. We hit enter and we see that we have a 1 there. So on your exam, in the real world, when you're calculating z-scores, always nice, do that little double check. Takes you very little time. Calculate the mean, calculate the standard deviation, and it will alert you to issues. If your mean does not equal or is not very close to 0, if your standard deviation is not equal to 1, there's an issue with your calculations, so you'll have that red flag to go back and check that out. All right, so that was for z-scores. Now let's finish up our Excel demo here by taking a look at part B, where they want us to calculate a new standardized score. So they want us to transform our old scores into new standardized scores. The first step we've already done, we've calculated out the z-scores. What we need to do now is we need to calculate out our standardized scores. So our standardized scores, we'll just call it stand-x. And for this, the most important thing to remember in this case is that you need the mean and you need the new standard deviation. You want the new mean, you want the new standard deviation. Look for those in the question. They need to be given to you. So here we say we want you to transform these scores into a new standardized score with a mean of 40 and a standard deviation of 10. And then once you have that, the last thing we need is we need that formula for raw scores coming from z-scores. And the formula is your raw scores equals your new mean plus the standard deviation multiplied by your z-scores. So we have the z-scores, we have our new mean, that was given to us in the question, that's 40. We have our new standard deviation, that was given to us in the question, that is 10. So we're ready to go, and all we got to do is pop that formula into Excel and let Excel do the heavy calculations. So we go to equals here, and this we need to manually enter because it's been given to us in a question. So our new score is going to be equal to 40, that's our new mean, plus your z-score multiplied by 10. 10 is your new standard deviation. We hit enter, and we have our new transformed standardized score of 57.5. I'll show you that one more time. Equals our new mean plus our z-score multiplied by our new standard deviation, which is 10. We hit enter, And then because we are only accessing those z-scores, we can copy and paste that all the way down, and we've calculated out our standardized scores. We're going to pop those into our answer cells here using the equals function. Extremely important to use the equals function here because that is carrying all your decimal places. We notice here that Excel has not displayed the decimal places. Just so that you know, they are there. Your decimals are there. And if you ever want to see them, it sounds like a threat, but if you ever want to see them, these little buttons up here allow you to increase or decrease your decimal places. So in this case, we want to increase our decimal places, and you can see they're all there. Excel hasn't forgotten about them. And down here, you can see that we got those all correct in our grading green cells. All right, but let's go back one more time and say that, let's say that this wasn't part of a demonstration. Let's say that you were in the real world, or very soon you're in an exam, and you just want to double check, you just want to make sure that you've done these standardized scores correctly. What can we do? Well, we can calculate the mean. We can go, all right, let me calculate the average of these new standardized scores. And what should the average of these standardized scores be? It should be 40. Because we were asked to create a new set of scores that has a mean of 40. So we can calculate the average, and lo and behold, there's the 40. We've done that correctly. It gives us confidence that we've not made an error anywhere. We can also calculate the standard deviation of our new standardized scores. And before we hit enter, we know that our standard deviation for this has to be 10, because that's what was asked for. We hit enter, and lo and behold, it is 10. So this is just a way of getting confidence that you have done this correctly, that you didn't make an error somewhere in either your formula or any other calculation, that you didn't use the wrong standard deviation. And that is when you don't have those standardized scores or those grading cells. All right, so what we're going to do now is we're going to take a bit of a break here, but I'll just wrap this up with a few pieces of information. So you have practice on this Excel sheet. So we have a bunch of questions here. There's 6 in total. Sorry, there's 4 in total that you can practice on to gain some more experience and basically familiarity. All right, well, hopefully this will work, but if it doesn't, we'll have an abbreviated version of this. Okay, so we still have practice that you can do, and I want to make sure that everybody is aware that the Z-score homework assignment number 5, chapter 2, part 3, that is not in my lab, that is available in Canvas. So we have 2 homework assignments that are only available in Canvas. They're all done on Excel sheets. This is the first one, so you can access it from Canvas, hand it in through Canvas, you'll submit it through Canvas. So just be aware that's where you find it. It's due Tuesday, May 21st at 12:15. So you basically got 24 hours to complete it after today's class. And again, that little bit of an anomaly in terms of the due date is just due to the exam that we have coming up on Wednesday. I'd just like to make sure that you have approximately like 24 hours, to hand it in, get your feedback, and get that all taken care of. For your homework assignment, very important, use, where'd you go? There it is. For your homework assignment, very important, use sample variance and sample standard deviation. So that it's all about samples in this one. On the exam, same thing, so we'll get you ready for the exam by doing that. So in the homework assignment, use sample variance and sample standard deviation. In terms of upcoming post-tests, chapter 1 post-test, we've had the pre-test, we've had the homework, we've had practice in class. We continue with sanding the floor, painting the fence by doing our post-test. Your post-test is due May 21st by midnight, and that is for chapter 1 and for chapter 2. Chapter 2 post-test is also due May 21st by midnight, so you can finish up your chapter 2 homework, and then you have time to do your chapter 2 post-test as well. And also, any pretest points that you're trying to earn by doing the My Lab study plan, by earning the mastery points. So you have to earn those mastery points. That's how you earn points to elevate your pretest scores. Just be aware that those are due midnight before the day of the exam. So if you want to complete those mastery points, the mastery points for Chapter 1 to be applied to your Chapter 1 pretest, those are due Tuesday, May 21st by midnight. And for Chapter 2, the mastery points for Chapter 2 to be applied to your Chapter 2 pretest, those are also due midnight by, May 21st by midnight. All right, so other than that, we are done with the first hour. And before we take a break, we'll take a break for, let's make this a longer one so you guys can practice up on the Z-scores. We'll break until 10:30, so like a 20-minute practice / break here. But I just want to reiterate that in terms of what is going to be on exam number 1, it ends right here. So we are done with Chapter 2. This is where your information for exam 1 ends. Now, because this is a summer session, we're going to have to continue on with class. So we are coming back at 10:30 to continue on with the course. However, everything after right now is going to be on exam 2. So once again, this is where exam number 1 ends. Chapter 1 and Chapter 2, frequency distributions, measures of central tendency, measures of variability, and Z-scores. That is exam number 1. So just so that you're clear on that, just making that announcement. But that's all that I wanted to cover pre-exam number 1. So we'll take a break now for 20 minutes. We'll come back at 10:30. I highly recommend try out some of these new Z-score calculations. Call me over if you have any issues, and we'll start up again at 10:30.